first term is 0 because f of x is sine of 0 is 0. Then we have x minus 0 divided by 1 factorial. I just don't need to put 1. This is the f prime of x, which is 1, plus x minus 0 square divided by 2 factorial. F double prime x, so that would be 0 plus x cubed divided by 3 factorial minus 1. Let's continue on the next page, next line. So x 4 divided by 4 factorial times 0 plus x raised to 5 divided by 5 factorial times 1 plus x raised to 6 factorial 0 plus x 7 factorial minus 1. Okay, so this is f of x, which is sine of x, right? So we can write sine of x is, see, let's see what terms go. This is gone, this has gone, this has gone, this has gone. So x minus x cubed divided by 3 factorial, or 6, plus x 5 divided by 5 factorial, which is 120, minus x raised to 7 5040. So that's the series expansion. Okay, so what's the use of a series expansion? Well, the whole point of trying to write a series expansion is to be able to approximate the function at some value. So that will be a second example. Let's see how good the series expansion is. So compute the value of sine of x at x equals 0.1 using second, fourth, sixth, eighth order terms. Compare your answer, compare against the actual value. Okay, so the easiest thing to do is to, well, let me just write it on a new page. The easiest thing to do is to write the actual value, which we know. We can find sine of 0.1. So the exact value is just sine of 0.1. Okay, so what is sine 0.1? So you can crunch it on your computer. I'm going to write it to, so it gives you, if you put it on your computer, it will give you, I think 13 decimal places, right? This is what I get. 0.998334166,468. Okay, now let's do with the various orders. So if you just go 2 orders, it's 2 terms of the series. So you'll have sine of 0.1. Okay, so what was 2 terms? If you go back, 2 terms means you picked up f of x and f prime of x, right? So you just go up to order x. So if you look at the expansion here, the solution we got, the first term was 0, the second term just was x, so it's just x. So this is x. So it'll be 0.1. If you go 4 terms, so if you go back and see this, what does 4 terms really mean? Well, 4 terms means you go 1, 2, 3, and then 4. So up to x cubed. So let's go and see what we have till x cubed. So x cubed is this, right? So it'll just be these 2 terms, x minus x cubed divided by 6. Okay, this comes out to be 0.0998833, and I'll put a bar there just to indicate that that 3 just recurs. It's 33333. If you do 6 similar arguments, if you do that, you'll get sine of 0.1 is x minus x cubed divided by 6. Yeah, I'm just going to put the value. It's 0.1 minus 0.1 cubed divided by 6 plus 0.1 raised to 5 divided by 120. And that comes out to be 0.099833416. And then we have 8 terms. And then finally, minus 0.1 raised to 7 divided by 5040. So this comes out to be 0.0998334166468. Okay. Okay, so here we have the exact answer. Okay, and all these answers, other answers are approximations. So if you just use one term, you get 0.1, okay, which actually is pretty good. 0.099 versus 0.1, right? It's like 10% inaccurate. And then once you start hitting 4 terms, you suddenly get like almost 4 decimal places accuracy, and just keeps getting better and better. So this just shows that a Taylor series expansion actually works. You don't really need to expand it so many terms. Now, here's the catch. 0.1, try sine of 0.5 this method, and you'll see that the accuracy will be much lower. Okay. Still, it turns out the sine is a nice, well-behaved function. So you might actually be surprised that sine, if you approximate sine of 0.5 as 0.5, right, if the first term, it's actually pretty close to the actual value of sine of 0.5. It's about 10% accurate. But then you get more accuracy if you go 4. So this works well, as I said, if you're close to the interval, and that's because of these higher terms. So if you see these higher terms, the contribution of the 8th order term is that raised to 7 divided by 5040. That's such a huge number that that term really doesn't really affect your calculation. So if you see a Taylor series where you do not see, you put a big number in the numerator, instead of 0.1, it was 100. Now you're in trouble. That thing is going to be significant. So you cannot estimate sine of 100, for example. It's going to be a very poor accurate estimate, because you'll have 100 raised to 7 divided by 5040, and that will just blow up. So you really need to be close to the value at which you expand to be safe. You want to be really close. What is really close is really a matter of checking out this way. For some functions, being close 0.5 is good because of that, the way the series expands set up. But for some other functions, e of x, for example, maybe even 0.1 or 0.5 may not be that good. Okay, now one thing we'll do is we should be able to get these answers straight from Octave. Okay, so we'll do that next. So how do we use Octave to get these answers? Okay, so here we're in Octave. I would work with the editor, that way I can save the file. Now I have no idea if I can do this in Octave, so I just use ChatGPT to see if I can even get something. There's a function which can be used. So turns out that for this particular problem, you need to expand something out. So it's not really a numeric value. So you need to do what is known as symbolic expansions. Have you worked with symbolic variables in MATLAB before? Anybody work with symbolic MATLAB? So when I say symbolic, when you define x, you say sine of x, it'll be recognized as sine of x and not as sine of 0.5. That's not a numeric value. Not worked in symbolic MATLAB? No, nobody. Somebody has. Okay. So it turns out in Octave, you need to do something special to get the symbolic stuff to work. What I'm going to do is, by the way, last class, I had given this prompt to ChatGPT and remember that. If you want, you can just continue over this, right? It basically remembers all your conversations so that way you can go back and refer to them. So maybe we can just start a new one. Okay, that's a new one. And so let's say series expand sine of x in a Taylor series in Octave. Okay, so it turns out that if you when you're using this for the first time, the symbolic toolbox, you actually need to go to Octave and type that pkg install forge symbolic. So you will take this and then literally copy paste it here. Okay, and then enter. So it'll install the package. You have to do it only once. Did I press enter? I don't know. Okay, so I've installed it before, but you will have to do it once to get symbolic to work. Okay, so going back, you need to say pkg load symbolic. That just loads the symbolic toolbox. Then say sims x and then Taylor sine of x, x order 10. So this one goes order 10, but we want to go order 8. So let's just copy this code. CLC clear all. And then let me save it. It's desktop Taylor. Okay, so let's just change this to 8 order. And then run this. So it loads the symbolic package and then it should print it out. Let's see what it does. Hey, that's a bit awkward. It just clipped off the x's. So we have a free package and that's what happens. So here's what you can do. Let's call this Taylor series this. And instead of printing it this way, I'm going to do it slightly differently. I'm going to say disp Taylor series. You'll not have this problem. By the way, you can run this code in MATLAB. We just comment out the pkg's load symbolic. You don't need that. So if you do it this way, hopefully it'll print it out in a way that we can read it. Okay, so that's what we had, right? It's written the other way. It's the first term is x, then it's x cubed divided by 6, and then so on. Okay, so it all looks good. Okay, we can always verify answers, and I highly recommend you verify the answers in your homework. Except that you cannot use this in the exam in the class, right? So you still need to know how to expand things out. Okay, now the other thing we asked was, can we actually find the value of this at x equals some value? So it turns out that you can do that. There's a command called subs. So you can do subs Taylor series. So this is the variable. I've assigned that expression to Taylor series. What I need to do here is substitute x as 0.1, right? And then if you run this, okay, so you did not print it, but let me do this. That's just weird. Oh. Okay, we need to find a way to do this. Maybe it's need to convert it to a double. By default, I think it's a symbolic. Maybe this will work. Nope. Think so it's interesting. I tried the same thing in on a MacBook, an Octave. It just works fine. It doesn't somehow give me the output in uh, Windows. Uh, yeah, it's going to rework the problem. I think it's just printed exactly what I did. I thought I did the same thing. Okay, I did print. Wow. It's exactly the same thing. Okay. I think it will not work this way. Okay, so it looks like there is some glitch uh, in the way Octave works. Remember, it's a free software, but if you do it this way, I think it'll print. Okay. Now this is only printing for 1 to 6 decimal places. If you want to print it longer than this, what you do is format long, and then you do this format long, and then this. Okay, so that's I don't know, 13 decimal places. Okay, so that's the answer. If you use Taylor series, order 8, and then you can check this answer against your answer. But if you want to do, let's say, we call this 8. That's the expansion to 8. But we could do this with just 2 terms, right? 2, 2. We call that 8. Okay, so again, I think it will not print it. Yeah, it doesn't print. But you could always do. Is there something wrong in the syntax? The code runs fine. It's undefined. Did I clear off anything? No, no. Okay. Yeah.
Can I see? Yeah, can you just stay on the? Can you just slowly scroll through the code again? I want to make sure because I'm getting error on 1. Give me 1 second.
Sure.
Thank you. Oh.
Okay, so we can do it this way. just make it value 8, the series. And then copy the same thing. Order 2.
Yeah, it's not working.
Not working. Let me just run this. Okay, that prints. And then okay, looks like this part of the code doesn't run for some reason. Okay, there, let me come move this out. Okay, now if you print value, we know that Taylor series expansion to order 2 is 1.1, right? To clear all. Okay. Okay, I think it was not clearing the memory, but hopefully it should work now. Oh, there it is, 0.1. And actually printed. Seems like what was happening was that this CLC, I always put CLC clear all. The clear all should remove everything in the buffer, but it doesn't seem like it was actually running that, was not clearing the memory, and that's why it was just printing the previous value. So that printed 0.1 as expected. So what I recommend is just trying everything out in Octave before you submit, so that way you know the answers are right. Okay, let's move on to, any questions? You got a code to work?
I wasn't able to get it to work. Would it be okay if you uploaded this on Blackboard?
Yeah, I'm going to do that.
Okay.
I do that all the time.